Well, good afternoon, everyone. My name is Macías. I come from the University of Coruña in Spain, and I am starting my PhD thesis about precisely the field you can see in the slide about property-based testing, non-functional requirements. So keep in mind that this is a work in progress, and so any kind of suggestions during the talk or even at the end are welcome, of course. And some of the concepts I'm going to explain and I'm going to talk about are redundant with the talk of John's talk. So I begin with a little introduction about general concepts, theoretical concepts about testing, then move to a classification about functional testing. What is functional testing? What tools we have in Erlang to perform this kind of testing, and then move to the non-functional side. We can talk about which kind of requirements fits into this scope. And finally, the more important part, I think, of the talk, the feedback and the open questions I have to answer among all of us. So the first question is pretty obvious. Why should we test software? There are a lot of reasons that all people here could say, but I selected the more important. I think they are. First of all, it increases the confidence in the code you are writing. Even that simple function that will never fail, we should test. We should write tests for that. Tests can be used as documentation, since we are writing the expected behavior of a system, so we can use as it, and helps to find bugs at earliest stage of development. But there are another important reason. Performing effective and efficient testing reduce the cost of the budget of projects. These two sentences are taken from the books, more or less. Probably John or Thomas can tell more about this, but they say more or less about a half of a project. The budget of a project is spent in testing activities. Another theoretical concept: successful tests are those that find bugs. We cannot prove that the software has no bugs. You cannot prove that the software complies the specification, and sometimes more testing implies finding less bugs. Another good practices that we should take into account when performing testing activities: test cases should be independent from each other. A test case should not affect to another one. Tests themselves should be repeatable, in the sense that we have to be able to run test cases when we want, and that includes every step of, for example, starting the system or creating the appropriate environment to the test cases. The test cases should be guided by the specification of the software. We should not take into account the implementation details that the software has. After testing, the system should remain as it was, and an implementation feature that the test code should be independent from the code itself. Some testing techniques that we can apply at different phases of the development process, or even we can apply them in combination. Static techniques versus the dynamic techniques. We can test software with running the system or not. White box and black box approach, meaning that white box refers to have access to the source code. Black box, you are just concerned about the inputs and outputs, or positive and negative testing. And finally, some typical list of testing levels. Unit testing refers to test a component in isolation. Integration testing, testing some components as a set of them and check the interactions between between them. System testing refers to check the system as a complete unity. And finally, acceptance testing refers to check if the business requirements are verified. But there is another classification depending of the type of the requirement we want to check. For example, we have functional requirements and non-functional requirements. The functional ones refer to what the software will do. For example, if we think a typical bank service where we can open an account, close an account, or deposit money in an account or withdraw money for them, maybe a functional requirement is that after calling create an account, we want that the software returns to us an identifier of the account. This is an example of functional requirement. On the other hand, non-functional requirement will be that it describes how the system will perform the functionalities that we are defining. For example, in the open an account, we want, for example, that the performance of getting the response time of getting the identifier is less than a value. For example, we don't want that the identifier comes to us 1 day after or something like that. What happens with this? That normally testing is identified by its functional side. It's the typical activities that we perform when we are doing testing. What kind of tools we have in the Erlang world to functional testing? Probably you know every of them. To perform unit testing, we have eUnit. The test cases are manually implemented as test functions. We have assertions to check specific values. I have a little sample here if you want to see. It's a simple example, the Fibonacci. And we have here different functions. We can group or not group the assertions we are writing, and to run this type of test, we just compile. In this case, all 9 tests pass. Well, we can, for example, modify here the expected value. In this case, as we expected, the expected value is 0, but the real value we get is 1. So, an example of how eUnit works. There are another framework which is Common Test. Common Test automates the execution of a list of functions, and it has a feature that we can analyze the past executions of the test cases, and is ideal for integration testing. Another features is that, for example, we can set up the suite with a specific behavior, or tear down the complete suite with another behavior. And I have also an example here. This is a simple adder. It spawns a process, and another process can send to the first one a number, and it adds the numbers the process is receiving. So an example of a test suite with common test. In this function, we put the test case we are testing. This case is a set of operations. And as I said, you can initialize the suite with some configuration, and the test suite with another one, and even for each test case. In this case, we want to start the server and add the PID to the configuration, and to finalize the test case, stop the server. So I'm going to make a mistake here to see what happens. we see that there is a bad match. We expect to have a -10 there. And an interesting feature is that the common test generates a web page where we can check the specific test case. In this case, failed with that reason, and the bad match is here. If we correct this -5 plus -5 is -10. So in this case, the test pass, and we can see here that the test case passed, and also we have track with the previous runs of the test case. For the people who attend the previous talk, this is redundant. In any case, our next step in functional testing was property-based testing. We can use declarative statement to specify the properties according to a specification. The test cases are automatically derived from the properties, and they are automatically run and diagnosed. QuickCheck or PropEr are tools to perform this kind of testing. The process: define the properties, run the test cases using the generators, and finally check if the properties hold or not. Another interesting feature, when QuickCheck finds a failing test case, it reduces to the smallest countersample that provoke the same error. The properties themselves are written in Erlang, so we don't need to learn any new language. And there are libraries to test a sequence of operations, as we saw in the previous talk with the process registry, and to implement a state machine to check this kind of systems. This is an example of the property. After applying the delete function to a list of numbers and a specific number, such numbers should not appear in the resulting list. And translating this to a property in QuickCheck is as easy as this. We say that for all I, which is an integer, and for all list, which is a list of integers, the integer I should not be in the resulting list after applying the delete function. These two are data generators, and this is the predicate we want to check. So we can sample this generator. I can do it. We had several lists of integers, and running the test cases means running the property. I have in the Emacs the property I showed to you, so we can run it. In this case, all the tests pass. If we run probably more times, we can find an error, but I'm not going to explain the internals of this. In this case, we have the -9 and this list with 2 occurrences of -9, and QuickCheck is bring them to the smallest countersample. However, the reason for this behavior, or we talk later, or probably you can attend the QuickCheck tutorial by Thomas Arts on Wednesday. So we agree that the functional testing is not enough in specific domains. For example, when the results are produced, when in specific domains, that when the results are produced or how long they take to be available can be very important. And normally these requirements arise at very later stages of the development. or what is worse, that when the system is yet deployed. There are a lot of requirements that can be in the scope of non-functional testing. For example, I told you about performance, about dependability or security aspects. There are a lot of papers and literature talking about this kind of requirements and the difficulty which is to implement a test for this kind of requirements. Another problems are that these requirements are generally informally stated, and it is difficult to keep a track of the test we have performed. So the question we wanted to solve, can we use property-based testing to these non-functional requirements? The work in progress I told to you is a library for a prototype of library to test non-functional requirements. And among all possible non-functional requirements that exist, I selected one of them, the performance, which is the typical one, the first requirement that arises when we are dealing with non-functional requirements. I'm going to check performance requirement using a black box approach. I just want to test the inputs and the outputs and the response time of that operation. And possible properties we can check is that the response time is less than a specific value, or the average response time of n requests of the same operation is less than another value. I have an example of the property. It's very simple. We give the module, the function, and an argument generator, and we check that the response time of calling that function is less than the value we provide. So I can use the previous example of Fibonacci. I call to simple performance, and I pass the module, the function, and in this case the argument generator is a large natural numbers. I implemented as big ones because I want to check the Fibonacci of bigger numbers. And I put that, for example, the response time should be less than 1 second. It is expressed in milliseconds here. So in this case, we get that the Fibonacci of 35, the response time is almost 2 seconds, and shrinking. After shrinking, we get that the smallest value to get more than 1 second is the Fibonacci of 34. This is possible because there is a direct relationship between the argument of Fibonacci and the response time is linear. In other cases, this probably don't work. Related to performance testing, we probably want to set a specific scenario of the system under test, for example, in a specific workload. So we could integrate these properties with another tools like Zoom or Megaload. Megaload is a tool that is under development in the context of an European project. So possible uses of this is you can, for example, set up the environment using the setup macro of QuickCheck, and to learn more about how to stress systems using stress testing, the Diana Corbach's tutorial on WASD probably will answer a lot of questions. And finally, another sample related to performance testing. Due to the internal implementation of the queues in Erlang, the queues in Erlang are implemented, probably you know, as two lists. After the response time of removing one element from the queue after a lot of insertions is going to be very high. And this happens, as I said, due to the internal implementation of the queues in Erlang. I can say you, for example, can create a there are two lists, and this is the module, the queue module of the distribution, the Erlang distribution. So there are some APIs. This is one function to insert the elements in the queue. So we can see the implementation. It goes to the in function. And we check when we insert the first element of the first element in a empty queue, then the first element is inserted in the first list. And when the second element, we insert a second element, so we move the first element to the second list, and we insert the second in the first one. And the third, the fourth, and the fifth insertions are going to match this clause. So, for example, if we have an insertion of 30 elements in a queue, the first one is going to be in the second list, and the next 29 in the first one. So, say that now we want to remove one element from that list. We can call to tail, which calls drop. So in that case, the clause we are going to match is this one. We have one element in the second list and another list in the first one, and this calls to rear to front. That when we have more than 3 elements, then we split the first list in two halves, and we reverse the second half of the list, and we put it as the second list, because we want to have access to the first elements, to remove it with a less response time. We can check here, for example, if I have a function to calculate the response time of calling to queue with that and an integer, for example. It takes 4 milliseconds in this case. So to check the behavior, to check that effectively after a lot of insertions, when we remove an element, the response time is very high, we can build a state machine. And in this case, the syntax is the old syntax of the QuickCheck state machines. The state is a queue with a limit. In this case, I put 30 milliseconds. Ideally, we probably want to calculate this in another way. The commands that we want to test, they are wrappers to the response time function. We call with a high frequency to the insertions and a low frequency to tail. And the next state of inserting an element, to speed up testing, instead of inserting one element in each iteration, I build a list of 30 elements and perform 30 insertions at one time. The preconditions just for the remove function, for the tail function, the queue has not to be empty, and the post conditions are that the response time we get is less than the limit we wrote. So we can run And here we see one example. We have a lot of insertions with a time of 2 milliseconds, in this case 1 millisecond, and when there is a lot of insertions, and we call to tail, then the response time is very high. Even the shrinking gets different values, of course, depends on the specific moment. So maybe this is a very simple example, but say that you, for example, have a software, a system with the data that process the data using a queue, and sometimes maybe the performance of some operations is very high, and we don't know why this happens. It could be for some reason like this. So the feedback we can discuss about is what other properties related to performance could be interested to implement. For example, we can simulate specific environments like increasing the memory, the disk usage, or the network usage. We can, for example, move to gray box testing in the sense of instead of have a complete system and check the performance of specific operations, maybe at integration level, at the integration testing, we can check the performance of 2 components or a set of components. What type of non-functional requirement would you like to have tools for testing it? In your experience in your daily work, and this is an open question. How could property-based testing helps when we are dealing with this type of requirements? So that's all. Thank you very much.
So questions, guys, and I'll pass around the microphone.
Does your library work the same with PropEr as it does with QuickCheck?
Yes,
it does.
It works.
It works with both. What about a lot of the load testing we do for performance stuff is across multiple nodes, and it's only when we've got loads of nodes generating loads of traffic between each other. It would be that kind of thing that would be really useful to be able to run this kind of testing on.
Yes, in fact, Megaload, the tool I mentioned before, performs some kind of testing, stress testing with a lot of Erlang nodes. So it's a very interesting tutorial to attend.
Hello, thank you for a good talk. I have 2 questions, if you don't mind.
Yeah, of course.
So the first one is that I actually in Haskell wrote a small add-on to QuickCheck for testing probabilistic distributions. So I was working on kind of random numbers, and it was a way of testing that the random numbers actually followed the distribution that it was expected to do them. Do you think that could be useful somehow?
It probably could be used. I don't know that library, so I will have to check that.
Okay, sure. And the second question is in all the examples you specified how much it could go from the distribution, like how much it could deviate from the distribution in a sense. Like when you were working with the queues, would it be possible to instead of supplying some kind of number to just detect if there's an outlier?
Yeah, that is the good thing that I have to do, because in this case I am supposing that the time limit is one that is not going to reach.
Yeah.
So probably that the initialization of that the state machine, maybe we can run a set of insertions and calculate the average of all the response time and put that value as the expected response time.
Yeah, exactly.
It's more realistic than what I have shown, but it's a work in progress. So
okay. Well, thank you.
Yes, it is in GitHub. NFR test live. I can show you after.
Thank you very much.